Okay, now we go to TS and PV diagram. It is important for you to know how to sketch PV and TS diagram of the Brayton cycle and also for Rankine cycle. Okay, so first thing first, we look at the component involved, compressor, and the state is 1 to 2. 1 is entrance of compressor and 2 is exit of compressor. This is combustion chamber where the heat will adding. And number 3 is state at the entrance of turbine, and 4 is the exit of turbine, and the gas will be discharged to the atmosphere. So we can sketch all the 4 processes in a TS diagram. So we can see here from 1 to 2 the temperature will increase. 2 to 3 in a combustion chamber the temperature is keep on increasing, and T3 is the maximum temperature. And when it go through the turbine, what happen is the temperature will decrease. Okay, so from TS diagram we know 1 to 2 is isentropic, so S1 is equal to S2. And also in turbine, S3 is equal to S4 because this is isentropic expansion. In 2 to 3, Q in, and 4 to 1 is Q out. This is PV diagram. Okay, from PV diagram, we can see this is isentropic compression in a compressor. What happened is the pressure increased from state 1 to state 2. 2 to 3 is in a combustion chamber, and this is heat addition in constant pressure. 3 to 4 is isentropic expansion, where we can see here that the pressure is decreased from P3 to P4. Okay, and 4 to 1 is the gas discharged to the atmosphere, Q out, and it happened in a constant pressure. So you have to know how to sketch TV and PV diagram, compulsory. Okay, and this is how we can simplify SFEE to find all the requirement that we want to use in the Brayton cycle. Okay. All 4 processes of Brayton cycle are executed in steady flow devices, compressor and turbine. Therefore, they should analyze as a steady flow process. And in SFEE, we neglecting kinetic energy and potential energy. Therefore, SFEE can be reduced to Q in minus Q out plus W in minus W out is equal to H exit minus H inlet. And please refer to SFEE if you don't familiar with this formula. Okay. So from SFEE, we go through one by one. First thing first, we look at the heat transfer to and from the working fluid. So heat transfer occurs at the combustion chamber and state 4 to 1. 2 to 3 is Q in, and the formula is H3 minus H2 if there is a liquid. But in Brayton cycle, we are interested in gas. Therefore, we convert H to Cp T3 minus T2 because it occurs in constant pressure. That is why we use Cp. Q out. Q out is H4 minus H1, and we convert H to Cp T4 minus T1. Next, we go to the work in, that is in a compressor, and work out in a turbine. So work in is H2 minus H1. is equal to Cp T2 minus T1, and work out is H3 minus H4, that is Cp T3 minus T4. Therefore, thermal efficiency of the Brayton cycle is familiar with the Rankine cycle, that is W net over Q in, and W net is W out, which is W of turbine minus work in. W of compressor is divided with Q in, or we can write the thermal efficiency of a Brayton with this formula: 1 minus Q out over Q in is equal to 1 minus Cp T4 minus T1 over Cp T3 minus T2. That's all for the simple gas plant for Brayton cycle.